Now, in this case, since z is zeta naught plus r to the power I theta, and what is zeta naught? What is zeta naught? Minus b epsilon. So, there is no imaginary part in zeta naught. There is no imaginary part in zeta naught. So, imaginary part comes only here due to r e to the power I theta. Okay. And this gives z minus theta is and what does it mean? What is the meaning of this? Z of minus theta is complex conjugate of z theta. What is the meaning of this? Say consider only a simple case r e to the power I theta. For this also this replication apply, this relation. What is r e to the power I theta? It is a circle, and for this also if we say z equal to simply r e to the power I theta, a complex function, then for that function also this relation holds, z minus theta is complex conjugate of z theta. Now, since z theta is a circle, what this relation, what is the implication of this relation, what do you say about circle? For what type of curve do you expect this relation to hold? Symmetric. So, it implies that the transformed geometry in this case, or whatever we are calling transformed airfoil, that is symmetric. So, the transformed airfoil is symmetric. So, in this case what we the geometry is a symmetric Zhukovsky airfoil, symmetric Zhukovsky airfoil, what we have shown earlier like this, a symmetric Zhukovsky airfoil. See, this also you can very easily see from the approximate relation x equal to 2 b cos theta, y equal to 2 b epsilon 1 minus cos theta sin theta. you can see that for theta and minus theta, the y values are simply plus and minus. The transform geometry is symmetric about x axis, symmetric about real axis. How much will be the chord length of this airfoil? Agreed? At theta equal to 0, it has only real value. At theta equal to pi also, it has only real value, and the difference between the two x coordinates, that is what is the chord length. And how much is it? Substitute all these expressions for x and y that we wrote earlier, you can do it, and the result will come as b into 3 plus 2 epsilon by 1 by 1 plus 2 epsilon. You can expand this in power series or apply your binomial theorem to find these 1 plus 2 epsilon to the power minus 1, and if you do this, this will come as b into 4 plus epsilon square plus still higher order term. And if we say that epsilon square itself is small, then this is equal to 4 b. Okay. So, the chord will be 4 b. What will be the maximum thickness? Please find out maximum thickness. If you want, you can use the approximate relation. The exact relation may be little difficult to handle, but you can use the approximate relation to find what is the maximum thickness. where it is and how much it is. How much? Use that simple relation y equal to 2 b epsilon into 1 minus cos theta sin theta. Use that. Yes, use this itself. Find simply where is y maximum dy dx equal to 0, where it is. At theta equal to pi by 4, we are getting maximum 4 pi by 3, 2 pi by 3, okay. And but theta equal to pi will give the minimum. At theta equal to pi, y 0. This gives maximum and this eventually gives minimum. If you want, you can check with second derivative, but by inspection itself we can say that at theta equal to pi y is 0, also at theta equal to 0. So, at theta equal to 2 pi, and what is the maximum thickness then? How much is the maximum thickness? How much is it? Yes. So, in terms of chord, the maximum thickness of this Zhukovsky symmetric airfoil is 3 root 3 by 4 epsilon. You have seen what is the significance of that parameter epsilon, what we have called the shifting of the center, the amount by which the center of the circle is shifted. So, that we have been able to find the flow on the airfoil, that is related to the thickness of the airfoil. So, if you know how much is the thickness of a Zhukovsky airfoil, you know how much you need to shift the center of the circle. By the way, on the airfoil, where is this maximum thickness? On this airfoil, where is the maximum thickness? Or where is this point theta is 2 pi by 3? Where is this point theta equal to 2 pi by 3? C by 4 from C by 4 from where? From the origin or from the center of the airfoil. Also you can see it is C by 4 from the leading edge of the airfoil. So, the maximum thickness of the Zhukovsky airfoil is at quarter chord from the leading edge. The maximum thickness of Zhukovsky airfoil is at quarter chord from the leading edge. At the leading edge, of course, the thickness is 0. So, from 0 to the maximum thickness it increases within a distance C by 4 and then again it becomes 0 from C by 4 2 at C. The other parameters like the velocity at different points, the trailing edge is clasped, that is already known. We have velocity at the trailing edge, how much? Compared to the flat plate, it is slightly reduced. For the flat plate, the velocity at the trailing edge was simply q infinity cos alpha. It is q infinity cos alpha divided by 1 plus epsilon. Epsilon is usually small because the airfoil thickness is of the order of say 10%. T by C maximum is of the order of 0.1. At any other point, of course, you can find using that general formula velocity on the circle divided by dz df. The complex velocity on the circle divided by dz df is the complex velocity on the airfoil. How much the lift coefficient? Let us see what is the effect of thickness on the airfoil lift. H pi a by c sin alpha plus beta, 8 pi a by c sin alpha plus beta. Oh, r by c, 8 pi r by c sin alpha plus beta. Beta is of course 0, r is how much? B into 1 plus epsilon. R is B into 1 plus epsilon, C is 4 B. Sorry. Beta is 0 in this case. So, it is 2 pi into 1 plus epsilon sin alpha. So, thickness marginally increases the lift curve slope. Thickness of the airfoil, as long as it is quite small, increases the lift curve slope marginally. Now, once again we will come back to the general case that we considered in the beginning. The general case we considered in the beginning, where the center is located neither on the real axis nor on the imaginary axis, but somewhere else. But that result also you can get it by combining these last two results, where you have shifted the center along horizontal and along vertical. A combination of the two will give the general shift, and then of course, you can see what will be the general result of the transformation. Because of the horizontal shift, we find a symmetric airfoil with certain thickness, certain maximum thickness. Because of the vertical shift, we find no thickness, therefore, is basically a line, it becomes a line, but it is curved line shifted with respect to the real axis or shifted with respect to the horizontal axis. See, if now combine these two, that is if we shift the center both vertically as well as horizontally, what is the shape we are likely to get? This is what is the last case we will consider under Zhukovsky's transformation. Eventually, we have considered this in the beginning itself. What it will be? Will it be a symmetric geometry? No. The symmetric geometry is available only when the center is lying on the real axis. As long as the center is lying on the real axis, the transform geometry is symmetric. Whether it is center and coincides with the origin or center is away from the origin, but if it is on the real axis, then we get a symmetric airfoil, symmetric geometry. If the center is shifted vertically also, we see that we have got something curved, which is called a camber line. So, when we shift both, what we will get is a camber airfoil, airfoil which is no longer symmetric about its chord, rather it is symmetric with respect to that mean line or camber line. So, if we shift therefore both and as before we consider this vertical shift. What we consider vertical shift last time? M equal to r sin beta and which is approximately r beta, and horizontal shift or we can call it the center is at minus b epsilon plus I m, that is the location of the center. point on the circle that corresponds to the trailing edge of the airfoil, point on the circle that corresponds to the trailing edge of the airfoil is at an angle minus beta, is at an angle minus beta, and the critical point minus b is placed on it. So, how much is that? Point on the circle plane that corresponds to the trailing edge point as before is zeta trailing edge. Be careful about the interpretation of this point zeta trailing edge. Actually, circle has no trailing edge. This is the trailing edge of the airfoil which corresponds to the point on the circle. It is not trailing edge of the circle. A circle has no trailing edge. How much is it? R cos beta minus b epsilon, isn't it? And this will sit at the critical point. This is what is our requirement. The transformed geometry once again you can get since zeta naught itself contain imaginary quantity, in this case this relation will not be satisfied, or the geometry will not be symmetric about the real axis or x axis. You can substitute here this zeta naught, which is r sin beta minus m, or m minus r sin beta, sorry, zeta naught is minus b epsilon plus I m, zeta naught is minus b epsilon plus I m. So, that you can substitute here and get the x and y coordinates of the transform geometry. However, if we consider very sorry. Looking to the earlier case, for the symmetric airfoil case, we see that the x has remained the same, meaning the chord length has remained the same. The expression for y, it has the same first part, but however, it has been added a term 2 b beta sin square theta, 2 b beta sin square theta. Which is positive always. Meaning with if we imagine a symmetric airfoil, then on the y coordinate there is a positive addition on the upper as well as on the lower surface. So, the lower surface is moving towards the chord line and the upper surface is moving away from the chord line, or the chord line is no longer a symmetric line of the airfoil, or the airfoil is not symmetric about the chord line. Rather, we have another line which is in between, about which the airfoil is symmetric, which is the mean line. The thickness of this airfoil can be obtained as thickness upper surface minus the lower surface. Upper surface is for theta equal to 0 to pi, the lower surface is from pi to 2 pi. Since it is sin square, so irrespective of the value of theta, this will give a positive number. So, when you subtract, this part will get cancelled, only this part that will become double. Once again you can find out what is the T by C max. T by C is this, 4b is C, T by C equal to epsilon into 1 minus cos theta sin theta, 4b is C. And you need not do it again, we have already done it, we can take that result from there. T by C max is 3 root 3 by 4 epsilon at quarter chord, which is C by 4 from the leading edge. The mean line can be obtained by how? How to get the mean line? How to get the mean line? Yes, the mean line about which the upper surface and lower surface are symmetric, the line about which the airfoil is symmetric. Yes, how to get the mean line or the camber line? We will for the time being call it say mean line or camber line, say y c, camber line y c is how much? It is the middle of the upper and lower surface. So, half of y upper plus y lower, and how much is that? How much it is? Add y upper and y lower, what happened? The first term gets cancelled, only the second terms remain for both upper and lower, and it becomes, that means it becomes doubled, 4b beta sin square beta, isn't it? It was 2b beta sin square beta, so it becomes 4b beta sin square beta. Okay. Oh, into half remains. Okay. Four b is again C, So, we can even write it as C by 2. Okay. Since our interest is always by C, so this. So, maximum camber or what actually call camber, maximum camber how much and where? Oh, this is not sin square beta, this is sin square theta, no? This is not sin square beta, sin square theta. Yes, maximum camber is obviously beta by 2, because sin square theta maximum can be 1, and where it is at theta equal to pi by 2, and where is that on the airfoil? What is theta equal to pi by 2? Y axis, that is at the mid chord, at the mid chord from leading edge. Usually is given in terms of percentage camber. So, percentage camber is beta by 2 into 100%. So, for Zhukovsky airfoil, as far as the geometry is concerned, we have seen 3 salient features. The trailing edge is cusp, the maximum thickness is at a quarter chord, and the maximum camber is at mid chord. What we have called as Zhukovsky's airfoil, which are very easy to obtain from circle, they are characterized by cusp trailing edge, that is trailing edge angle is 0, its maximum thickness is at quarter chord, and its maximum camber is at mid chord. These are of course not very good characteristics for a real airfoil. Usually a cusp trailing edge is not desired, even it is very difficult to manufacture compared to a finite angle airfoil, extremely difficult to manufacture. And also as far as the overall flow characteristics are concerned, an airfoil which has a maximum thickness at so early at quarter chord, you see it is increasing its maximum within 25%, then decreasing it over 75%, remaining 75%. And so, that is also not a very good or desired characteristics or desired property of an airfoil. Similarly, maximum camber so behind at mid chord is also again not desired. Usually the airfoils would like to have all these things at around something near about 35 to 40% in that area. Maximum thickness is not at 25%, rather 35 to 40%. Maximum camber is also somewhere in that range, 40% or so. That is what is preferable. So, in that respect, Zhukovsky's airfoil are not a very good candidate for practical airfoil to be used in aircraft. However, but only that type of airfoil this Zhukovsky's transformation can give. There are some other type of transformation, I mean rather there are many transformations which can give airfoil which are more suitable. I mean having trailing edge angle non-zero, having thickness somewhere little behind, or having camber little ahead. Even you can construct transformation where you can have many parameters by which you can fix all these as much as you want. I mean you can take those as parameter, like I want the maximum thickness to be at 35%, I want the maximum combat to be at 38%, I want the trailing edge angle to be 2 degree. All these things can also be specified. Of course, the transformation become complex. However, you remember that Zhukovsky's transformation, the simplest transformation, but not the only transformation. There are many other transformations which can be used, and we can get different type of geometry or any type of geometry that we want. Of course, as your requirements becomes more stringent, the transformation also becomes more complex. However, as you have already mentioned that this Zhukovsky's transformation or any this complex transformation, which is a very good technique to find flow very easily, is restricted only to 2 dimensional flow. You cannot extend it to 3 dimension. So, for other practical purposes also you must need to look into some different type of approaches, which are valid say for 2 dimensional any given type of airfoil to any 3 dimensional shape. So, there are many such methods, and some of those methods we will be covering at different stages of this course, may not be in this particular course, but its continuation courses. What would like to point out one more thing, that we have seen that in all these theory, whether we use this Zhukovsky's transformation or any other complex transformation or any other complex method which can solve the flow for any given geometry, the result that we are going to get will always be lift an acceptable or realistic value, drag 0. That is true, as long as we are restricted to that equation Laplacian phi equal to 0, the drag force that we are going to get is 0. No matter whatever complex method or whatever sophisticated method that we try to solve it, we are not going to get drag equal to 0, unless we bring in something else. So, what we would be rather doing, we will try to do a little bit, of course, again we will leave something of that also for a later course, that is what is the technique by which we can get something of the drag also. This gives a lift which is quite acceptable, What we have found that lift is more or less lift linearly varies with angle of attack as long as angle of attack is small, that is quite acceptable. If the airfoil has a camber, then the 0 lift angle of attack will be somewhere at minus 2 times that camber, that is also realistic. Even that lift coefficient CL equal to 2 pi into 1 plus epsilon sin alpha plus beta, or 2 pi into 1 plus epsilon alpha plus beta for the general case, that is also realistic. It gives a very good approximation of the lift coefficient. So, as far as lift is concerned, we are satisfied more or less that okay, whatever we wanted we are getting good lift. What we can get in an experimental measurement, what we are getting is very close to it, within maybe 8 to 10%, and the lift coefficient for airfoil or wing type of geometry is rather high, and so within 8 to 10% of this is quite all right, but the drag coefficient is always 0. So, we will try to see that what is the reason why we got drag equal to 0 and how to avoid that situation, how can we estimate drag. At the very rudimentary concept of that we will try to focus, but before that we will of course complete this transformation by certain numericals. So, perhaps next 2 or 3 lectures we will dwell on some numerical examples, and then we will move to look for non-zero drag. Okay.